So last video we actually stopped here, stating that the dxi is equals to this equation over here. Okay, we also state the new definitions for u and v. Okay, so there is two types of definitions for u and v. This is u and this is v. It's in terms of xi, partial xi divided by partial y. Okay, while another definition is from here for the pathline itself. So they are actually related, but I can't explain well. Nonetheless, let's come over here. So we have last stopped over here, right? So so from equation 1, which is this one, we know that dxi is equals to 0, right? Because as you can see, this eventually this is equals to 0, right? Because when you bring the v dx over here, you're minus, right? So you're left that portion here equals to 0, and therefore knowing that knowing that u equals to, we can sub u as equals to this. I mean, yeah, nonetheless, and also to this, and then since yeah, nonetheless, after which you become like that. Okay, because you're partialing xi partial y dy. Okay, because you're trying to differentiate the y portion away. Okay, I already explained, I don't want to explain again. So if you wonder why it's partial y and dy, you can actually check back my previous video. Okay, I explained to you and you can think about it. If you understand, you can just skip. You can continue with my part. Okay, so my part over here now is actually to because since we know that this is equals to 0 and this is equal to dxi. Okay, so this thing is equals to this thing. Okay, because u is simply partial, so if you sub u over here, simply this is u and this is minus v, and they are the same thing. You see. So in other words, we can say that dxi is equals to 0. Okay, since u dy minus v dx is equals to 0, then because u is equals to this, so this portion is another representation of this portion. That's all, finished. So in other words, dxi is equals to 0. Hope I made this very clear. So therefore, if you integrate both sides, okay, in terms of xi, you know that xi is equals to some constant c, and this constant c is a streamline, is a value of streamline. Okay, so if you want to visualize actually how streamline is, okay, I'll just show you. You remember last video we should actually talk about streamline is actually a tangent, to the velocity vector. Okay, tangent to the velocity vector due to u and v. Okay, so therefore I have the graph over here. So this is actually this is the plot of a streamline, different streamlines. Okay, so the xi itself, is the streamline value. And how does this streamline value works? Okay, so how does this streamline value works? So before I were to go here, maybe I should do an example first before I come here. So hold on. Let's talk about this thing first. Okay, the velocity profile of a two-dimensional fluid field is given by the vector, velocity vector is equals to a constant, x. Okay, and then this I hat is the x direction, saying that it's going in the x-axis, and then y, and then this is saying that it's going in the y direction. So this is it's a pretty simple equation. So where a is equals to 0.3, so consider the flow is incompressible. So it is linear. I mean, yeah, a steady and non-Newtonian. So it's pretty much easier to talk about it. So obtain an equation for the streamline. Okay, obtain an equation for the streamline. So how do you actually do it? So I actually do have this done. So you know the streamline equation is this one, the one that you have first been exposed to, dy over dx equals to v over u, right? So So where v is equals to all these things, okay, I've explained earlier. So therefore, given this equation, we are given that this equation, okay, you know that because I don't want to confuse you later that the v hat, I mean this v vector is different from this v. Okay, so that's why I put O. So we call this O vector, okay, a velocity vector. So this is actually velocity of the fluid. Okay, just don't want to confuse you with the v in this case. That's all. Okay, so this is the equation. I just rewrite all the initial condition. I just rewrite this part, but changing this alphabet v to O only. Okay, so to solve, we identify what is actually u and v. Okay, so we identify that u is equals to ax. Okay, so u is equals to ax. So it's just a times a multiplied by x. Okay, and then v is equals to a multiplied by minus y. So this is actually, if you remember, so this portion here, because you are talking about velocity, so velocity wise, you are in terms of the x-axis velocity and y-axis velocity. So this is why we're talking about u and v, as u describes the x-axis velocity, while the v describes the y-axis velocity. Okay, so this is why we choose u equals to ax and v equals to minus ay. So taking the streamline equation, okay, so you know that the equation itself is v divided by u, okay, and therefore dy dx is simply saying that minus ay is divided by ax, because v is equals to minus ay, right? So you just put it over here, and then u is equals to ax, so you just put it over here. Okay, so therefore it is equals to minus y over x, right? Because you cancel away the a's. Okay, a are constant, and then you rearrange for separable equation using this stuffs. Okay, so they're all equals. So I just bring the x, I just bring this dx out, and then I'll just bring this y. So eventually you'll get a 1 over 1 over minus y and 1 over x. And then you do some integration. Okay, it's a simple integration. 1 divided by minus y is equals to 1 over x dx. So in other words, this is this. Okay, so ln minus ln y is equals to ln x plus some constant c, we call it ln c in this case. And then you rearrange, you can bring the minus ln x over here, and then so because it's negative, so you just factorize out, you have, because ln y, if you factorize out the negative, so you have a plus, right? And then since you know that logarithm, if you ln y plus ln x means that ln y multiplied by ln x in a certain term, so it's ln yx. Okay, so I mean ln y plus ln x is equals to ln xy, that's all. And then since there's a negative, we just bring it over, and since this is a constant, the constant we don't know what is a constant, so we just put a negative, and so you bring the negative over here, it can be a constant, it cannot be. So in other words, a constant is just a constant, just who cares if it's negative or positive. So we can call this thing ln yx is equals to ln c, because who cares if it's negative or positive, right? The constant is just a constant. And then another c equals to xy. Okay. In other ways to put this is that if you were to bring this minus ln y over here, and then you bring this ln c over here, and then because this will be plus, and then we will have the same result. Okay, it's the same thing. It's just the arrangement, and you have to be very careful with the arrangement. Therefore, you have this thing. Okay, nonetheless, the concept is who cares the constant is negative or positive. So from this, you can actually see that c is equals to xy. So what is c actually? C is a streamline. Okay, if you remember, we actually took v divided by u. You remember v divided by u is the equation to calculate streamline, and eventually we actually have this constant c equals to xy. So what is this constant? Okay, this constant is the same as my constant that I have just derived earlier, saying that xi is equals to z. Right, we're taking that the integrate d xi is equals to integrating the 0. So if you integrate 0, you have some constant. So this constant is in terms of my xy. So this is why when we do this one, you have no idea how the general equation can apply to, right? How these things can be applied. So in the next few parts, and then we'll talk about it. I mean, in the next few lessons. I mean, next few videos. But nonetheless, the concept is there. So since you know that the streamline is equals to xy, so our streamline in this case, okay, in this scenario, streamline equation may be some other equation, maybe x square, maybe x cubed y square over 2, just random. So different streamline constant will give you a different type of flow. So in this case, for xy, you'll have this type of flow over here. It is a plot. Okay, so this plot itself is the x. Okay, this is the velocity, is the u. Okay, in a sense, and this is the v itself. Okay, actually, hold on a while. Okay, I'm plotting this thing x. Okay, the value of x and the value of y. I'm plotting it with the value of x and the value of y. So at maybe there is no time in this in this graph itself. So at when x is 0.2, okay, y is at this position, so we have here. So when x increases, the y actually drops, and eventually you have this curve over here. So the relationship is that imagine we have this is the xy, okay. So if our xy value is, so if our streamline value is 1, okay, if it's, because c equals to xy, right, so if it's 1, then I set x, the growing of the x, okay, as you can see, the growing of x, okay, sorry, so my x value is over here actually, so as you can see I put a lot of stuff, so x value and all these things over here. Okay, it's an equation. Later I'll just derive the equation. Okay, imagine you have this equation to describe x. So x itself is an exponential curve. Okay, so if you plot all these points into so correspondingly, if you were to divide 1 divided by x, you'll get y, right? So if 1 at this time 0, okay, 1 divided by, let's say our x is 0.2, right? Our x value is 0.2, at time 0 is 0.2, because we want to find y eventually, because we are setting x as our moving part. It's a little embedded type of thing. So anyway, so if it's 1 divided by 0.2, you have, where do we have? You have 5 over here, right? If it's 1 divided by 0.2, you have 5, right? So if x is 0.2, then y is 5. So therefore, with this relationship, we can plot the graph. So if x is 0.2, our y is 5. And then if x is if x is 10, if x is 0.4, sorry, hold on again. Okay, sorry, my fault. So okay, in this case, in a certain sense, that in this point, okay, imagine there's a line over here, right, touching all those points. This line is actually when the time is x is proportional. In other words, at time 1, okay, although this is not, because this equation, I mean this axis is in terms of x, okay, in terms of x. However, because x is plotting against time, so let's say because Let's show you. Okay, our x can be plotted in terms of an equation like this. Okay, 0.2 EAT. Okay, this is how I actually plot it out. So when t is equals to 1, okay, or t is equals, okay, when t is equals to 0, it's 0.2, right? So it's actually shown in my option over here, 0.2, correct? So this is why at 0.2, different magnitude of the streamline will have different graph. Okay, so if at streamline 1, okay, at streamline 1 divided by 0.2, we have 5. So streamline itself is a gradient of the x and y, but you cannot see over here. This is why it's very hard to convey my information. And then nonetheless, if its streamline value is 2, 2 divided by 0.2, 0.2 comes from my equation as I said earlier. If t equals to 0, okay, we're still talking about t equals to 0, you have 0.2. So therefore, if you know that the streamline equation is c equals to xy, right? So if c is equals to 10, then x divided by 10 divided by x, since this is 0.2, right? So 10 divided by 0.2, it's 10. I mean, what the hell? 2 divided by 0.2, sorry. What am I talking? In this case, the c is actually 2. Okay, so if c is 2, this is 0.2. If you were to divide, 2 divided by 0.2 is actually 10. Okay, so it's actually shown in my graph over here. So y value is 10, so this is what we have over here. I hope I make this clear. Okay, so at time 1 is this point, is this line. At time 2 it is, so in this case you can say that the trajectory of at time whatever is moving in this direction. At time, this is time 1. At time maybe at time 0, okay, at time 0 that is in this thing. Okay, at time 0, because we said that at time 0, 0.2, because e to the power 0 is 1, right? So 1 times 0.2 is this. So at time equals to 0, okay, we will have this. We will have all these points over here: 1 point, 2 point, 3 point, 4. So as you can see, 0.2 is in terms of the equation x. Okay, so at time 1 is this one. At time 2, where you cannot see from here, but rather than you can see from the equation, using the equation at time 2, so it will be like 2a e to the power of 2a times 0.2. So you have some x value and then you plot it over here. So at time 2, you may have some values with this line. So you are plotting against all these things. So this is why I say that this is plotting against x and this is plotting against y. While x grow with time, because I take x as a certain variables to it's just, so this is why it is, so this is why we are actually talking about the how do I say, the complicated part in trying to convey. So I hope I give you an understanding that this is actually the x position, this is the y position. With the x position and the y position, you can plot the point where the particle is, the position of the particle. So this at time 0, the particle is over here. At time maybe maybe at time 1, time 2, okay, you will have some position over here. Time 3, time 4, time 5, time 6, you have some position over here. So this line will correspond to a lower streamline value, okay, streamline constant I would say. So this, as you can see, c in our case is c equals to xy, right? So the lower you are in our case, okay, you have so this is the lower value you are at the lower point. So if let's say you are higher, so this is the streamline value of 2. So c is equals to 3, and then c equals to 4, and then c equals to 7. So you can see as you increase your streamline value more, you'll actually move the graph higher. So in this case, I say you put 20, okay, And then I just, you see, you can, so 20 is this point over here, you can see it's moved. So I hope you got what I mean. And then in the next video, we'll just continue. So see you.